Our world basically runs on autopilot. Every single second, countless decisions get made without a single person lifting a finger. Think about a factory floor, or even the power grid. It all just works. But how? Well, today we're going to pull back the curtain on one of the simplest, yet most critical, little pieces of tech that makes it all happen. It's the unseen hero of our automated world. It really all comes down to one basic question. How does a machine, a pump, a motor, an entire factory make a simple choice? An on or off, a yes or no decision? How does it know when to start, and maybe more importantly, when to stop? The answer, it turns out, is a lot simpler than you might think, and it's been hiding in plain sight this whole time. And here it is. This is the microswitch. I know, it doesn't look like much, right? But this little guy is a mechanical marvel. It's the physical version of a yes or a no decision. This is the unsung hero of our story, and trust me, it is absolutely everywhere. Okay, so to really get why this thing is so powerful, we have to start at square one. Let's break down the most basic job of any switch. Just making the simplest decision you can possibly imagine. The best way to think of a switch is like a gatekeeper. That's it. Its only job is to send one of two messages to some kind of controller. Could be a computer, a motor, whatever. In the digital world, we call that a binary signal. It's either a 0 or a 1. It's either off or it's on. And this is a perfect way to picture it. On the left, the switch creates a gap. The circuit is open. That means electricity can't get across and the light stays off. That's our 0. But then, when the switch is flipped, it closes that gap. Now the circuit is closed, electricity can flow, and boom, the light comes on. That's our 1. See? Super simple. Now this leads to a really important idea. Every switch has a default state, what it's doing when nobody's touching it. A normally open switch, or NO for short, is off until you do something to it. A doorbell is a perfect example. A normally closed, or NC switch, is the exact opposite. It's always on and it only turns off when it's activated. That's what you want for something like an emergency stop button. Okay, so that's all great, but what if you could take the human out of the loop entirely? What if a switch didn't need someone to press it? What if it could feel? Well, that's where we get to meet the pressure switch family. So instead of a button for a finger, this switch is hooked up to a pipe, and it's constantly sensing the pressure inside. And when that pressure hits a specific level, a set point as the engineers call it, the switch flips all by itself, sending that on signal to the rest of the system. So what's the big deal? Well, these switches they can feel have 3 huge jobs. First, they can monitor a system, right? Sounding an alarm if pressure gets too high or too low. Second, they can protect equipment, shutting a whole process down before something breaks. And third, they can just control stuff, like telling a compressor to kick on when the air in a tank runs low. And of course, just like any tech, they've gotten way better over time. On the left, you've got the old school electromechanical kind, full of actual springs and moving parts. And on the right, you've got the modern solid state version, no moving parts at all, which means they're incredibly precise and last a whole lot longer. Some of these switches are even cooler. This one is a contact pressure gauge. So not only does it do the whole switching thing at a set point, but it also has a dial right on it. So an operator can just walk up and see the exact pressure in the system. It's a switch and a gauge all rolled into one. Okay, now this part is a really clever bit of engineering. Let's say a switch is set to turn on at 100 psi. What if the pressure is just bouncing around right at 100? The switch would be flickering on, off, like crazy, and that would absolutely destroy whatever it's controlling. So they invented something called the deadband. The switch might turn on at 100 psi, but it won't turn off again until the pressure drops down to, say, 90 psi. That 10 psi gap, that's the deadband, and it's what keeps the whole system from tearing itself apart. So far, we've talked about how these switches make things run smoothly, but now we're going to see where this little device becomes a literal lifesaver. This is the switch on the absolute front lines of industrial safety. I want you to picture some of the most dangerous workplaces on Earth. An oil rig out in the ocean, a deep coal mine, a chemical plant. What's the one thing they all have in common? They're all places where one tiny spark could cause a massive disaster. And yeah, you see that last one? A sugar factory? Fine dust can be just as explosive as gas. The danger really boils down to a simple concept, the fire triangle. To get a fire or an explosion, you just need 3 things: a fuel source, oxygen, which is just in the air around us, and some kind of heat or spark. The huge problem in these dangerous places is that two of those three things are pretty much always there. And that fuel isn't always what you'd think. Yeah, it can be obvious stuff like flammable gas, but it can also be a fine cloud of dust from grain or wood or even sugar. When that dust is mixed with air in just the right way, it's basically a bomb waiting to go off. So here is the massive problem. You need electricity to run these places. You need lights, motors, and, yep, pressure switches. But any normal electrical device creates tiny little sparks inside it while it works. In a normal room, who cares? But in one of these hazardous areas, that little spark is the third side of the triangle. It's the ignition source. The only way to solve this is to build the equipment so it is physically impossible for it to create that spark. So how on earth do you do that? I mean, you can't just cross your fingers and hope for the best. You need a rule book, a global set of standards to make sure every single component is designed from the ground up to prevent a disaster. And that's where these global standards organizations step in. In North America, you've got groups like NEMA. Internationally, a big one is the IEC. These groups have spent decades writing incredibly detailed rules for how to build equipment that can be used safely in these dangerous places. Here in the US, for example, the National Fire Protection Association, the NFPA, literally writes the codes that say how to design buildings and install equipment. Their entire mission is to stop these kinds of industrial accidents before they can ever happen. Which brings it all back to our hero, the pressure switch. The switch you'd find on an oil rig is not the same one that's in your house's water system. It's built to what's called an explosion-proof standard. It's basically sealed inside a tiny fortress. So even if it does make a spark internally, that spark can never, ever get out and ignite the air around it. So when you trace its journey, from just a simple little gatekeeper for ones and zeros, all the way to the super smart sensory device, in its most important form, the pressure switch is a silent guardian. It's an unsung hero that is constantly on duty, keeping people and places safe in the most dangerous environments we have. It really makes you wonder, doesn't it? As our world gets more and more automated, what other simple, overlooked little gadgets are out there, quietly doing the most important jobs, keeping everything running, and keeping all of us safe? Something to think about. Thanks for joining me.